Today, I will introduce to you two similar super-resolution microscopy techniques, photoactivable localization microscopy, PALM, and stochastic optical reconstruction microscopy, STORM. Now, before we dive into the principles underlying these two techniques, let us first describe the motivation behind the development. Traditional light microscopy is hindered by what is called the diffraction limit of light. The diffraction limit describes the smallest feature size that an optical image system can resolve. Now, note that the diffraction limit is driven solely by the physics of light and is not based on the manufacturing limitations when building microscopes. In fact, back in 1873, a German physicist named Ernst Abbe realized that the resolution of optical imaging instruments, such as microscopes, is fundamentally limited by the diffraction of light in what he later represented as Abbe's law of limiting resolution, where lambda is the wavelength of light used and Na the numerical aperture of the imaging lens. This is essentially the diffraction-limited resolution of an optical system. If all aberrations and distortions are eliminated from the optical system, this will be the limit to resolution. In reality, if aberrations and distortions are present, they will determine the practical limit to resolution. For visible light emission, the optical resolution limit in the XY plane is somewhere in the range between 250 and 300 nanometers for a high magnification microscope system. Though this seems already small enough, we are still 2 orders of magnitude higher than the length scale of a typical biomolecule of interest. Still worse, the resolution limit along the z-axis is even higher. This presents a large problem since many biological processes are characterized largely on the nanoscale. Luckily for scientists, several key methods have emerged in the recent years to address this limitation. PALM and STORM were introduced separately by two different groups in 2006. At a higher level, PALM uses a photoactivable fluorescent protein, while STORM uses a pair of synthetic dyes such as Psi3 and Psi5, which exhibits a switching property when the fluorophores are closely located. Although the fluorescent probes and the technical details are a bit different, the principles for constructing a super-resolution image are the same, and both techniques can be categorized as localization microscopy. The main reason for the limitation of spatial resolution in fluorescence images obtained by conventional wide-field microscopy is the overlap of the fluorescent spots on the camera. This is inevitable as we try to record the fluorescence from each probe at the same time. Mathematically, each fluorophore in a biological sample is associated with a point spread function, and extensive overlap between the point spread functions of neighboring fluorophores will cause blurring during image formation. In PALM and STORM, point spread function overlap is avoided by a temporal separation technique, with only a small fraction of all the fluorophores activated at any single time point. Over multiple time points, say several thousands in a typical experiment, a final super-resolved image can be generated from the accumulated centroidal points. So, you might be wondering how we can possibly get a sparse subset of fluorophores to be activated at a given point in time. A key innovation offered by these two super-resolution techniques is their use and control of the photoactivable, photoconvertible, and photoswitchable properties of certain fluorescent protein labels in the case of PALM, and of antibody-targeted inorganic dyes in the case of STORM. For example, a commonly used photoactivable fluorophore in PALM is photoactivable green fluorescent protein, or PAGFP. PAGFP undergoes a single transition from a non-fluorescent to a fluorescent state upon light-induced activation. Over a course of a single PALM experiment, photoactivable fluorescent proteins such as PAGFP are continuously activated, imaged, and then photobleached to temporarily separate molecules that will otherwise be spatially indistinguishable. In most experiments, it is also desirable that fluorophores immediately bleach following activation in order to eliminate the presence from multiple acquired images where they would augment the probability of particle spatial overlap. A strong excitation light is then applied to bleach the fluorophores, but the cost is increased phototoxicity. STORM, on the other hand, exploits the photoswitching properties of fluorescent dyes such as Alexa 647 when in close proximity to a secondary fluorescent dye label such as Psi3, which functions as a fluorescent reactivator after bleaching. In this coupled type dye pair, Alexa 647 is a reporter, which emits a fluorescence upon a red laser illumination during which it forms a dark state, and Psi3 is an activator, which helps the activation process under green laser irradiation. In both cases, PALM and STORM, a flexible palette of fluorescent proteins and dyes is offered for various scenarios, giving us the ability to describe biological systems with new radical detail. There are, however, some shortcomings to be aware of for PALM and STORM. For both PALM and STORM, high sensitivity is necessary to detect individual fluorophores. This is because the signal from one fluorescent molecule is very weak, and typical photoactivable fluorescent proteins allow fewer than 1,000 photons detected before photobleaching, for example. Organic dyes using storm are only slightly brighter, but the detected photon number is still smaller than 5,000 in most cases. Further, the acquisition times for both palm and storm are very long, often requiring tens of thousands of frames to get a single image. In this video, I provided an overview of only 2 out of many super resolution image techniques. It is clear that these Nobel-worthy techniques have opened up a whole new world of potential biological discoveries, and hopefully this video has convinced you well enough to start adopting super resolution as a powerful tool in science.